So I want my, I've got zt is h of xt. So again, just like in a standard calculus class, you would basically take this and look at a bunch of a partition of the real line of width delta. And so I would do this for t equals delta, 2 delta, 3 delta, 4 delta, and so forth. Sum up both sides. I'd have this for every time. And I'd get an integral. That sum would be like an integral. So I get something like your Riemann-Stieltjes integral, although not really. And then what the hell happens to that? You know, as I let delta get smaller and smaller, what happens to this thing? You know, well, what ends up happening is you're summing a bunch of almost independent random variables. You know, all of which have a variance of delta. You know. And sigma of xt times delta, you know. And with a lot of work, you can show this actually becomes deterministic. I mean, the noise here is gone. You know. Oh wait, did I lose something? Yeah. No, I didn't. I almost lost something here. I've got the 1/2, the h double prime, the sigma's there, but this thing here, I know it's random, but you're summing a bunch of random things. It's like the law of large numbers. The variability is insignificant compared to the non-random part. Okay, so that's a bit of magic. Again, that would this was an SDE course, you'd devote a week to this. And you'd use a lot of martingale tricks. Basically, there'd be there's a lot of meat there. But that dt is dwt squared. So let me write that down. If you look at the very first page of McKean's book on Brownian motion, he writes that down. That dwt squared is dt. It's a formalism that you can justify and get results like that. All right? Okay, so we've got a few minutes, right? Yeah, so this is really like mad. I mean, what the hell are we talking about here? We got to bring this back to something a little more concrete. What this really means is, you know, what do I mean by the integral from 0 to t of f of xt dxt? Wait a second, no, I made a boo-boo somewhere. I wrote f. Look. See what I mean? That's why I said I wish I'd done this in a different color. I was grabbing equations. I grabbed that equation instead of that. It's h prime dx. Sorry, people scream. Okay, one of you must have noticed that. All right, one of you must have noticed that and was too shy to say it. Don't be shy. All right, please look at this. Look at this. It's right there too. Look, it's correct. I've got h prime of xt dxt. All right. All I'm doing is interpreting that. This is just like when you learn calculus. When you learned this change of variable formulas of calculus, you just did that, and you sum both sides. And you had h prime of x dx. All right, we're doing the same thing. All right, h prime of x dx. All right, let's plug that in. So dxt so I'm writing down the code and then I want to interpret it, okay? And so you just plug it in. All right. Okay, so this is still code, and now let's put it all together and make sense of it. Pretty much code. We've got, I'm going to take this and plug it in. You see I've got a dt term there and a dt term there. I'm going to collect the dt terms. So I've got a f times h prime. And then another one here with the second derivative. Plus a martingale.
So that should be a sigma squared, right?
Probably. No. Did I put? Oh no. There's no sigma square there. Yeah. Right. I mean, our original differential equation was that we wanted x dot to be f of x plus sigma w dot. And what's the martingale? The martingale is the term right there. So I ignored the part with the dw in it. So the part I dropped was this so there's a sigma of x times h prime. Okay, and there we have. So that's a zero mean martingale. All right. And it has the same properties as before. If I wanted to compute its variance, I would end up integrating the square of this. I mean, just like before. Again, I'm surveying a semester course in an hour, so I mean, I just want to give you the main punchlines. What would you do with this? Like in calculus, you do this because you'd like to understand the trajectory h of xt. You know, you understand exponentials and logs, and you want something else. What happens in probability? What are the kind of questions you ask? You know, x of t is a position of some robot. You know, and it's being pushed by noise. You know, you'd like to know. Yeah, stability. Is the robot stability? Oh, thank you. I wanted much less than that, but yes, stability. You'd like to know if xt is crashing off to infinity or not. Boy, did you get it right. This is the key to stability theory of stochastic systems, which I wish I could get into. I might touch on this now that you mention it later on. But even a more basic question is it where I want it to be? Well, not exactly, there's noise. So what's the standard deviation? So you'd like to get moments, you know? And so it's really useful to have this representation to get moments, because this has zero mean. All right? This has zero mean. So we have a differential equation basically for moments. So we can take the expectation of both sides of this thing, and we get the expectation of, say, h is a moment, like the second moment maybe. You know, it's the second moment times 0 plus some integral. Now that involves some other things that are funky, but if you set things up right, you can computer estimate the quantities inside, and this is zero mean, it disappears. All right? So this thing here turns out to be really, really a big deal. Oh, here there's a, here there was, I'm sorry. Here there was a typo, right? The sigma squared, I dropped a term there. Is that what you're referring to?
Yeah.
Oh, I'm sorry. Whenever you see an H double prime, yeah. Here was the transform. I'm sorry. Here, I was mixing these up. Yeah, absolutely. Thank you. Yeah. No, absolutely. We have a sigma squared here because of this. Yeah. So you'll see this a lot. This is called the differential generator. And if you want to look at stability of dynamical systems like this, this is the foundation. You just play around with the differential generator. And again, if you want to get bounds on moments and things like that, you play around with the differential generator, because that's all we've got inside this bracket, is we're looking at the differential generator and then dropping in the process at time r and integrating. You know? So we're integrating the differential generator applied at xr, and then plus a zero mean term. Yep.
So is F just like the nonlinear system applied to the state?
No. Remember what F was? I mean, F.
Clearly defined F.
Yeah, no, I did. It's right there. It was our model.
Yeah, so it's just a nonlinear model.
You know, it's a vector field. Yeah. So we have a nonlinear system, and that's the vector field. Right? You know, in a control system, typical thing, this would be linear. You know, f of x would be ax. You know, that's the most common example of this. And we all know if that were the case, then if fx was just ax, we know the eigenvalues of a have to be the left half plane. And yes, it's true. If if you have f of x equals ax, then the second moment of xt is bounded. If and only if the eigenvalues of a are in the left of the real part, yeah, strictly negative, for every eigenvalue. And the proof is by messing around with these guys, with this thing. And now you've convinced me. I'm going to give you a homework problem with this. Yeah, I was contemplating that already, but it's not hard. It really isn't hard. Take a linear system and take h to be quadratic. It's just no problem at all to get to see this. But I'll do in one dimension. I won't torture you with a vector value problem. All right. Okay. Yeah. Thanks. Any other questions? That was But it was good. It was good. You all know what an SDE is now. We've practiced martingales. About 10% of you are going to look at continuous time stochastic models in the future. And I'd be very happy you saw the differential generator once in your life before having to dive into a more technical book. All right. So have a good weekend, and we'll jump into Poisson processes and all that next time, and then into filtering.